G'day guys, Socket here. Today's video is a small extract from the speaker specifications what do they mean tutorial. Now instead of having to trawl all the way through that 3-hour video, I've pulled this piece out as a standalone little extract so it's easy for you guys to find. Now today's topic is on speaker frequency response and speaker limits. Now it's got a fancy title, but it's a really important video to understand because it explains that when, or explains why when you do a full range measure of your speaker with no crossovers or anything like that, that the speaker tends to roll off at the top end and at the bottom end of the frequency range. So, why does your speaker do that, and why is that important when you're setting crossovers, and all that type of stuff. So that's the topic of today's video. So let's dive in and take a look. Alright, let's take a look at frequency. So as you already know, the range of human hearing is between 20 and 20,000 Hertz. So a Hertz is 1 cycle per second. So at 20 Hertz, that means the speaker cone is moving in and out 20 times a second. And at 20,000 Hertz, it's moving in and out 20,000 times a second, which is incredibly fast. So in car audio, we use different speakers to play different parts of the sound spectrum, right? So subs to play, the low bass, and tweeters to play the very high frequencies. And of course, when we're doing our tuning, we use crossovers to limit the frequency range the different speakers play, and we allow a certain amount of overlap so that there's a transition between, for example, the tweeters and the mids. We have this thing called a crossover region, so you guys are kind of all familiar with that stuff. But if I overlay the speaker sizes, across this frequency chart, you'll notice that at the high frequencies we use very small speakers, 1 inch, 2 inch, and down at the very low end we use very large speakers, 10, 12 or 15 inch subwoofers, right? But why is that? And the answer to that is because different frequencies have different wavelengths, right? So a wavelength is nothing more than the sine wave of a particular frequency, completing its 360-degree phase cycle, is 1 Hertz, and at 20 Hertz, right, at that particular note, this distance or this sine wave or sound wave is wavelength, I should say, is 17 meters long, right? It's huge. At 300 Hertz, it's 1 meter. At 3000 Hertz, it's about 10 centimeters. And at 20,000 Hertz, it's about 2 centimeters, right? So very, very small wavelengths at this end, very large wavelengths at the low frequencies, right? Fantastic. So, but what's that all got to do with different speakers? And the short answer is when we look at speakers that we need for high frequencies, we want them to be able to create very fast, tiny movements because they're going to move back and forth thousands of times per second, right? So very, very small movements. They're not going to move a lot of air. They're moving very, very quickly. And therefore you only need a very tiny cone, very little excursion, very little power, and they produce very little heat, right? So that's the characteristics of tweeters or speakers that play very high frequencies. Whereas down at the other end of the scale, the lower we go in frequency, the slower and the bigger the movements need to be. We need the cone to move more air per stroke, which means that we need bigger cone area and bigger excursion. And because we've got more mass in the cone and we want to move it further on each stroke, that means we need more electrical power. More power means more heat, which means more cooling. So, as we go from high frequencies to low frequencies, the amount of air we need to move, the size of the cone and the mass of the cone, the power needs and the heat generated all increase as you go from high frequencies to low frequencies, right? But why can't we just have one speaker that can play the entire range? And the answer to that is because speakers have limits, right? All speakers have a high frequency limit and a low frequency limit. Now, there are speakers called widebands where this this usable frequency is very wide, but even so, all speakers have these high and low limits. So let me explain what these limits are and how they kind of work. Okay, let's say that we have a 6.5 inch and a 3-inch speaker and we want it to play 1000 hertz. Now, at 1000 hertz, we want the speaker to move back and forth 1000 times a second. And so if you think about it, a 6.5 inch speaker has a big cone and a big excursion, it can move back and forth with big strokes. So getting this speaker to move back and forth 1000 times a second means the motor has to push all of this weight, make it brake, make it sort of reverse direction very, very quickly. And so it's got a big throw. It's going to be difficult to move back and forth quickly, whereas the little 3-inch with its much smaller cone and its much smaller excursion, maybe it's 4 mils or something like that, then this is going to be able to move back and forth much easier than this big 6.5 inch, right? And so if we want to play 1000 hertz, then the 3-inch speaker is got better design characteristics than the 6.5 inch for this particular task. So all speakers have what we call a high frequency limit, right? That we call the cone breakup point, right? So if we think about our 6.5 inch speaker, there'll be a point where the motor can only push it back and forth cleanly before it starts to distort and have problems, right? And that is basically the cone breakup area point, right? The 3-inch will do the same. Like if you try to play it too high, it will reach its cone breakup point as well, right? But the cone breakup point is basically where the cone is no longer in control. You're trying to accelerate it faster than it's designed to, and it starts to bend and flex. And because certain points of the cone are at different relative positions to each other, that means that you start to get distortion and phase issues and things like that. The motor is trying to accelerate and brake the cone faster than it's capable of, so you start to get reduced output. And of course, as we talked about earlier, inductance rises with frequency, which means that for the same power, the voice coil is becoming more resistant to current direction changes, and therefore you get reduced output as well, right? So all of this is happening as you approach and pass this high frequency limit. And we can kind of see this in the frequency response and impedance curve when you look at your speaker technical data sheets, right? If they provide this this little plot. So in black is the frequency response. You can see that it's kind of falling off around about here. The output starts to take a huge nosedive, and that is because of the inductance, which is here in red, starts to go up. The cone acceleration, or the moving mass acceleration, starts to fall off, and the cone bends and flexes, and we start getting all this beaming and distortion and other things kind of going on. So you can kind of while it's not 100% clear on this graph, but the cone breakup point for this speaker's somewhere in this area, right? Somewhere in there. So that's what we call the high frequency limit. Okay, so let's just take our 6.5 inch and our 3-inch speaker, and this time we want it to play 100 hertz. Now 100 hertz compared to 1000 hertz is a much lower note, and to play lower notes you have much bigger wavelengths, and therefore you need to create more acoustic energy, which means more power, moving more air with every stroke of the speaker. So what that means is if you're using more power, you're going to be generating more heat, you need more air moved per speaker stroke, but the strokes are much slower. So if you think about little 3-inch, it's going to be now moving, compared to 1000 hertz, it's going to be moving 10 times slower. The cone area and the excursion of the speaker cone hasn't changed, however, but at some point, this little 3-inch is not going to be able to move enough air or deal with enough power to play super low notes, right? When you compare that to the 6.5 inch, which has a much bigger cone area and is able to extend further, which means it can push more air per stroke. It has a bigger motor, so it's more powerful, so it can push more air, and it's able to deal with much more heat, right? So, the same way as we have a high frequency limit, we have a speaker with a low frequency limit, and in the case of low notes, when you're looking at 100 hertz, then the 6.5 is going to win because it's got bigger cone area, bigger X max, and a bigger motor, stronger motor that can push more air and deal with more heat, right? So between the two, this is going to be the winner to play lower notes. And it's the reason why you find that, mids and tweeters don't do hair tricks, right? Because they just simply can't move enough air. So this lower limit, right, is what we refer to as the X max. You can push your speaker beyond that, but we're going to get, once again, declining sound quality and distortion and things, and lower outputs. And yeah, so what's happening here? Well, first of all, the cone is reaching its excursion limit, right? So the ability of the cone to move the air needed to play a low note, there's a physical limit of that, right? The little 3-inch can only move so far, right, and push so much air per stroke. And so you hit that limit, and if you try to keep pushing, you just get less and less output, right? And to move all of that air, you need more power. More power means more heat. So the more you try to push it, the more heat you generate, and eventually you end up with thermal failure, right? The adhesives in the speaker start to melt, or the voice coil burns out and fuses, or whatever. And we kind of looked at this a little earlier when we talked about X max and X mech, right? So yeah. But once again, when you look at the frequency response graph and the impedance curve, you can kind of see, you can kind of see with that point where the speaker starts to enter this area and the output starts to drop off, right? So in a nutshell, all speakers have a low frequency limit and a high frequency limit, right? There's a point where they can't play notes any lower because they run out of excursion, or they start to hit their thermal limit, right? They can't handle the power that's required to play that note at a particular frequency. And at the other end, they reach a limit where they can't oscillate any faster to produce a high frequency note, right? They get to a point where the cone starts to break up, and the impedance and that type of thing starts to reduce the output of the speaker, right? So there's this usable frequency range that all speakers have, and it's called the pistonic zone because the cone is working as a piston. It's nice and smooth, it moves back and forth, and it's basically where the speaker is operating within its thermal and mechanical limits, and therefore you get the best sound quality and the best loudness, right? So when we're doing our full range measures, we can kind of see where these lower and upper limits kind of are. So here's a full range measure of our tweeter, and yes, we have a 1000 hertz crossover put in there to protect it from over excursion, because as you go lower, excursion increases. Tweeters have very tiny excursions. If you make the tweeter play a low note, it will cause the membrane of the tweeter to flex too far, and that's how you end up damaging your tweeters. But anyway, that aside, when we do a full range measure, we can kind of see where these upper and lower limits are, right? This is where we're asking the tweeter to play higher than it can, and you can see the output just drops off, right? Because you've reached the cone breakup area of that tweeter. It cannot vibrate any faster than it. This particular one drops off at 14,000 hertz or whatever it is, and same on the low end. It gets to a point where it can't play any lower than that because of its excursion limit, right? And the same with our mids, right? You can see here where the upper and lower limits of the mids are. It starts to fall off. And you start getting more distortion. And the same with our subs, right? it won't play lower than that, and it won't play kind of higher than that, right? So all speakers have this this natural high and low frequency limits, and you can, as I said, you can see them when you're doing your full range measures, and this is the reason that we put crossovers in around about this point, to stop our speakers, to keep our speakers playing in their nice operating range, and stop them from playing, outside of that operating range, if that makes sense. Okay, so I just want to talk about different speaker configurations in car audio systems. So take a typical system like a excuse me, a three-way and a sub, so tweeters, mid-range, mid-bass, subwoofer, and they're all playing, the intended frequency range that they want to play. Now, I always say that the most important speakers in a car audio system are the mid-bass and the mid-range. They do most of the musical, the heavy lifting. The tweeters add a bit of sprinkle, detail to the top end, and the sub, gives the extra boom down the bottom end. But they kind of add something to the sound stage. They're not the entire sound stage. Most of the sound stage is between these two speakers, right? So when it comes to a three-way with no sub, right? Let's get rid of that for a minute. Yeah, I mean, the system will play fine. Of course, you won't have the boom of the low bass, but it will sound pretty good. You might even be able to push your mid bass down a little bit, right, to get it a bit lower. But without a sub, it's going to be musical. It just won't have that super boomy low end, and you just got to be careful not to try to push your mid bass down too far, because it's going to reach the excursion limit, and if you do, it's going to sound boomy and terrible and distorted, and you're just going to put your mid bass at risk of thermal damage, right? So what about a two-way system, right? Two-way system with no mid-range, so I'm going to get rid of the sub because it doesn't have one, and doesn't have a mid-range, so let's get rid of that. So this is quite popular with manufacturers that are selling component systems and people that want to run a two-way system with no speakers. So they'll often have the mid-range playing way up here, and they'll have the tweeter playing, way down low to try to meet it. Now, I'm personally not a big fan of that. I much prefer three-way systems, and the reason for it, as we just said, right, this mid-bass will play 1,000, 2,000 hertz, whatever it is that the crossover is going to be, but is it going to be as clean and as nice as if it was being played by a speaker that is the right size to play it? Now, I know you can buy component systems where the mid-bass and the tweeter, are paired, to do this. And yes, as I said, it will play, but will it play it as nicely as if you had a mid-range, right? Maybe not. So often people come to me for help with their two-way systems, and because they'll have a huge dip in the middle here somewhere, right, where the mid-bass and the tweeter are struggling to cross over properly, and I see that quite commonly. So is there a problem with running a two-way system like this? No, absolutely not. If you're pressed for space, or you don't have enough channels on your DSP, or for whatever reason you want a two-way system, then certainly nothing wrong with it. In fact, if you buy a component system where these things are supposed to be matched together, then provided that everything is installed properly, they should cross over. Just be aware that while they can play like this, doesn't mean that they play this region particularly well. All right, let's move on. So two-way with a sub and no tweeters, right? So what would that look like? So we'd have our sub, we'd have our tweeters, don't exist. It would typically mean that we try to get our mid-range to play a bit higher, and maybe have our mid-bass play a little bit higher, but not always. No, let's not do that. Let's just put that back. Let's say we do that, boom, like this. Now, often, once again, the problem is that you'll have all this end of the spectrum is fine. Of course, we won't have the super sparkly, tweety details. You might get this to play up to 6,000, 7,000, 8,000 maybe. but you won't get that top end detail. Unless you try to push your mid-range to play way up here, which you're probably going to run out of. Cone's probably going to break up because they're not built for vibrating at 8, 9, 10,000 times a second, right? So quite often these will be wideband speakers. They'll have specs that say you can play from 50 hertz all the way to 20,000, or something like that. But same as the previous example, they might be able to play that. Will they play them well is another question, right? So widebands are normally, they won't be 4-inch. They're probably 3-inch or maybe even 2.5-inch, and they're a compromise, right, between a tweeter and a mid to try to get a mid-range to play super high. But once again, you can have a decent system with it. You just be aware that the top end is going to suffer, right? Okay, so they're just like some of the common systems that people might be running. Three-way system with a sub, or a three-way without a sub, or a two-way system, just mid-bass and tweeters, or maybe a system without tweeters and using a wideband to cover that kind of top end, right? Nothing wrong with any of these systems. They just have different compromises. In my opinion, the best setup is a three-way with a sub. Just because the speakers are designed to play these specific ranges, right? They'll do it effortlessly within their proper operating band. Just pointing that stuff out. Okay, so when you're buying speakers and stuff like that, well, how do you work out what frequency range the speaker will be playing? And it's a bit tricky. You can kind of look that up on the technical data sheet. You'll have maybe the frequency responses listed, and this one is 60 hertz to 5,000 hertz, right? So that's a pretty broad range. As I said, it can play it, but is it going to play it well? That, according to this spec, that is the operating range of this particular speaker. So you can either read it off the sheet. You can look at the shape of the frequency response graph and kind of eyeball it. You can look at the FS of the speaker, or maybe the you can read the FS off the over here, 2250, or look at the impedance peak. There's lots of different ways to get an indication from the technical data sheet about the frequency range that the speaker might play. Now, just bear in mind that this has all been done in a lab. And so real life and how the speaker will play in your car, depending on where you've installed it, how you've installed it, whether it's in free air or in a box, or how much breathing space there is behind it, and all of that type of stuff. It may look different. So here is a real life example. Here is the technical data sheet. Here is the plot, and here is the actual measurement of the tweeter, in my particular location. So this thing's kind of rolling off here at about 3,000 hertz. It's pretty close there, but you can tell that the curves are not identical, and that's just because of the way that they've been installed, right? And that changes. So there you go, guys. I hope today's video helped explain what's happening when you're looking at your full range measures, and why you don't want to try to push your speakers too far beyond the natural limits from where the full range measures indicates that they want to play. Now, a lot of people that do car audio tuning really don't understand this concept, and they push their speakers way too far. They end up wondering why their system sounds distorted and kind of muddy and blurry, and this is a big reason for it. So I hope you enjoyed today's topic. If you've got any questions, please feel free to throw them down below. Otherwise, guys, thanks for watching, and I'll catch you in the next video.